Welcome to the Walton Pi. Today we're going to be talking about what measures are, what measurable spaces are, and what measure spaces are. All of them mean something slightly different, but they all look like relatively close to each other when you're just looking at it. So all of these are in one video today, and I'm going to cover all of them for you. So to start off, a measurable space is a pair of a set and a sigma algebra on that set. And then a measure is a function, mu, defined from the sigma algebra M to the interval 0 to infinity, where it can reach the value of infinity, satisfying 1, the measure of the empty set is 0, or mu of the empty set is 0, and 2, for a countable collection of pairwise disjoint sets, so the set of EIs where I is a natural number, the EI and EJs, they are their intersection is empty whenever I and J are not equal. And then this property is called countable additivity, where mu of the union of these pairwise disjoint sets is equal to the sum of the measures of those pairwise disjoint sets. Now this is only true, very important to realize this is only true all the time when these sets are pairwise disjoint. If they overlap, this is almost definitely not going to be the case. Now, confusingly, if we just change the infinite condition on the countable additivity to being just finite additivity, then this is what's called a finitely additive measure. And confusingly, even though the word measure is in there, this is not actually a measure. Okay, I've gotten tripped up by this before. I know lots of other people who have gotten tripped up by this before. Remember, a finitely additive measure is not actually a measure. And then lastly, a measure space, that is a triple, where X is your set, M is your sigma algebra, and then mu is a measure on that measurable space. Okay, there's also several different types of measure spaces. So if the measure of the entire space X is finite, we say that mu is a finite measure. If we can write X as a union of sets, all of which are finite measure, and it only took countably many of them to do so, then we say that mu is a sigma-finite measure, so it's the union of countably many things of finite measure. An example of a sigma-finite measure is a lot of standard measures on the real numbers, where you're able to write the real numbers as a countable union of intervals. Each of those has finite measure. And then the last type of measure space that we're going to talk about today are semi-finite measures. And this is where for any set with infinite measure, there is some subset of it, F, that is measurable, so it's in your sigma algebra. And also 0 is less than the measure of S is less than infinity, so it's a non-zero but still finite measure. In that case, we say that mu is a semi-finite measure. Let's go over just a couple examples. If X is a set and F is a function from X to 0 to infinity, then what we can do is we can say that the triple X with the sigma algebra of the power set of X, and then mu F, where I'm going to define mu F in a second, that is a measure space where mu F of some set E is equal to the supremum over all finite subsets of E of the sums of the F of X's, where X comes from that set. So it's a little bit tricky, but this is saying, okay, if I have a set and I'm looking at all the different points, I can evaluate the function at each point. I'm going to take every single possible finite collection of those points, I'm going to evaluate the function on that finite collection, and I'm going to add all of those up. If we take f of x to be 1 everywhere, then this is the counting measure. If a set has 27 elements, it will return the value 27. If a function, or if a set has infinitely many elements, whether that's countably infinite or uncountably infinite, it's going to return infinity. And the only thing that gives 0 as an output is the empty set. So this is what we call the counting measure. We could change the function, so we could start by picking some x naught and then define the function to be 1 at just that point and 0 everywhere else. Then we say that mu f is the point mass, or the Dirac measure, at x naught. So this returns 1 for a set E if E contains x naught, and it returns 0 if E does not contain the point x naught. Another example, if x is an uncountable set, and then we let M be all countable and co-countable sets. Co-countable just means its complement is countable. Then mu, given by mu of E, is 0 if E is countable, and mu of E is 1 if x minus E is countable. This is a measure on the measurable space Xm. Now if we take an infinite set and let M be the set of all finite or cofinite sets, so where either E or x minus E is finite, then mu, given by mu of E, is 0 if E is finite, and 1 if x minus E is finite. That is a finitely additive measure that is not a measure. So remember when I mentioned finitely additive measures earlier are not measures? Here is a specific example of something that looks like it might be a measure, but is actually just a finitely additive measure. I hope this video was helpful. If it was, please like and subscribe. It really helps me to be able to keep making these videos. And you are always free to check out some of my other videos and leave comments if there's other topics you want me to cover. I hope you have a great rest of your day, and good luck with all of your math.